everyone, and welcome back to my YouTube channel. Today we will be discussing routing. Let's dive in. Alright, so what is routing? It is the process of determining paths across the network for data to travel from source to a destination. It ensures data reaches the intended destination efficiently. How does routing work? Well, it uses routing tables. Routers use a routing table to store the paths, the routes that they know to predict. They use routing tables to store routes to reach destinations that they know, whether that be manually configuring it using a static route or dynamically using a routing protocol or dynamic routing protocols like OSPF, EIGRP, RIP as EGPs or a BGP, or excuse me, EGP, exterior gateway routing protocol, like BGP, to share information about the network topology and available routes. Path selection. Routers evaluate routes using metrics and select the most efficient path for data packets. Forwarding packets. Once a route is chosen, packets are forwarded to the selected path to reach their destination. Why do we have routing? It is essential for efficient data transfer. Routes packets along the best path to minimize travel time and congestion, and it enables communication to different networks. Different methods, facilitating global connectivity. It supports network growth by managing increased traffic without overloading infrastructure. It can also provide redundancy by providing alternate paths, ensuring stability and uptime if one route fails. And this is an example. So of redundancy. So source device here, and then this is the destination device. It can go through here, and then it can also be load balance through here, and then it can be here. So multiple ways of providing redundancy and load balancing tracking. Because let's say this one's really fully congested, or about to be reach its limit of fully being congested, it's able to then make a decision which path is less congested, send it here so it ensures that it arrives as fast as possible. And this is an example of the routing table. As you can see here, the codes say how the route ended up in the routing table. It can be local connected, which are automatically populated in the routing table once it's an IP address. Static is only manually configured, and then the other ones are looks like they are through dynamic routing protocols. So here it's going to tell you the routing type. C is for connected, L is for local, S is static. And then here the AD or administrative distance is a key indicator of what dynamic routing protocol they use to actually receive it. And you can change it as well. I'll show you that later. And the next hop, it just means so if I send it to here, it's going to get to this destination here. Like some analogies are when you're in church and you have they pass around the basket for you to put your money in there to get to the church. You know it starts at one end of the road, but you know it has to get to at the other end of the road that you're sitting in, right? So all you know is if you pass it to the person next to you, it's gonna get there. Or let's say you're passing notes in class, right? You have to give it to Jerome, right? Who sits on the other side of the class. But you know if you turn around and pass it to Einstein, he's gonna end up passing the card to Ricardo, Alex, right? Tony, just so that it can get to John on the other side of the classroom. So all you need to know is where to hand it off to, right? Like football, right? I think it's the running back, if I'm not mistaken. You just hand it off to the running back and you know it's going to get to the end zone, right? But yeah, so it's going to say this, you can read it by this route was learned statically to this destination network. This is the administrative distance, and if I pass it to this address here, then it's going to get to this network. Routing metrics are values used by routing systems to advance path for data packets across the network. Common metrics include hop count, bandwidth, delay, reliability, loading cost. Purpose. Metrics optimize traffic flow by prioritizing faster, less congested, and more reliable routes. Different routing protocols use one or more metrics to calculate the most efficient path. And then types of metric, up count, counts routers hops on a route, lower count indicates shorter routes. Bandwidth measures link data rate measures link data rate. Higher bandwidth supports more data and reduces congestion. These are some of the other ones as well, right? Administrative distance is a measure to use to determine how reliable a routing source is. So the lower an administrative distance is, the better and more likely it's going to be used in the routing table and system routes, right? And trustworthiness of the route may have overlapping routes on within the network. Within a network, and it uses AD to decide which route to take. And here is the routing protocol and the default AD. So let's say you have EIGRP right here, ISIS, OSPF, a static, and a local connected route. Based on what we talked about earlier, which one would you think that the router will select? So it will select the connected route, or the connected/local. Why? Because the administrative distance is 0. Remember, the lower the administrative distance, the more trustworthy it is, and the more it's likely to be selected to actually route traffic. Right? So connected routes. Connected routes are routes automatically created by a router for networks directly attached to their interface. When a network is directly connected, the router instantly adds it to its routing table. Priority connected routes generally have a higher priority than other types of routes, ensuring direct access, no configuration needed. Since through direct connections, no extra configuration or routing protocol is required for these routes. Local routes are routes represented on the router's own IP address interface. IP address assigned to its physical interface. Right? That's the difference between local. So this would be the actual IP address on the interface, and then this would be the network that it connects to. The network, the interfaces are residing in. These routes are added to the routing table as soon as the interface is assigned an IP address. Purpose, they allow the router to identify its own addresses for communication within the network. High priority. Local routes have highest priority, ensuring efficient handling of traffic to the router itself. Now, default routes/default gateway. Default routes acts like a catch-all. It's the least specific route. So if it doesn't have, so let's say you get a route for, let's say 192.168.15.3, right? The router will check its routing table. If it sees that it doesn't have anything that, if it sees that it doesn't have a route to that network, then it will use a default route, which is the least specific route. So a catch-all, right? It's going to send it to that route. Typically used for the internet, right? When there's no other specific route matching a destination. It's to direct unknown traffic to a specific gateway, usually towards the internet or a larger network. Only one default route is needed to manage traffic for all unknown destinations. Common use is often used by routers to forward traffic outside of local networks to an ISP. Routing types. There are different types of routing protocols out there, such as, and each has its own pros and cons. There are also different types of routing types. One is called static routing, and the other is called dynamic. Some of the different types of routing protocols: OSPF, EIGRP, RIP, ISIS, BGP, static routing, etc. There are more routing protocols, but each have their own purpose. And this is it. So local is identified by L, automatically added when the ports are configured and given an exact IP that is there on the device. Connected, automatically added again. The ports are configured, but only shows the subnet that is configured. And static or manually configured on the device which creates routing points. And then these are the dynamic routing protocols that we spoke about earlier. And then let's get into static routing. So static routes are manually configured routes set by a network administrator. Right? So someone has to actually go into the device, whether that be through a console port or using the V2Y lines using SSH to actually configure them. Right? They provide precise control over routing paths, ensuring traffic follows a specific routes. No protocol is needed. Static routes don't rely on routing protocols, making them simple and stable but require manual updates. So if there's a slight change in the topology of the network, you have to go in and manually change it and update the static routing table. The use case is ideal for small networks or specific paths, and larger networks like secure backup routes. Purpose and use cases of static routes: ensuring as a fallback path if dynamic routes fail, ensuring continuity. Small simple networks, ideal for small networks without complex routing needs. Simplifying setup and management. Secure dedicated connections, providing fixed paths for VPNs or secure links, enhancing security and control. Isolated or specialized networks directs traffic to specific subnets or isolated environments for precise traffic flow. Configuring a static route. So, identifying the destination and the next hop, determine the target network and then the IP address of the next hop router. We'll actually do a lab on this that I have here already, but we'll get into that. Okay. Right, so you do this in global config mode, right, with the command IP route followed by the destination. So where you're trying to get to, the subnet mask, whether that be a /24, what else, 24, 27, 30, right? And then the next hop. So where can I hand this over to get to here, right? Remember the analogy of when you're in church, you just pass it to the next person and you know it's going to get to the end of the row. Or when you're passing notes in class, you know if you hand it off to Eisner, it's going to get to Jerome, right? Just like that, right? And verify the route. Check the routing table to confirm the static route is added correctly, and then ping to test connectivity. So two-way communication, right? This is very important. Two-way communication that ping confirms the destination to ensure that static routes function as expected, right? Because in a network, what typically happens, there's either two things that happen. One is the device, there's two devices, right? Now let's just simple this up. So let's say I ping from here to here, right? So I'm here, I ping. So this is where the two things happen. Either this router is unable to communicate with this router, or this router is able to communicate with this router, but doesn't have a way, or router 2 doesn't have a way to communicate with router 1, or router 1, excuse me. So those are the two case scenarios, right? Where either they don't have communication at all, or it's just one-way communication. And that's why ping is very important and an essential troubleshooting technology for testing full two-way communication and network connectivity, right? So, and the next hop. The next hop is the immediate router or device a packet is sent to on its way to the destination. Ensures packets are forwarded in the correct direction, especially in multi-router networks. The next hop must already be reachable and should be directly connected to the router for this to work. Verification. Confirm next hop is reachable by checking the routing table and testing connectivity. And then I think this is what, let's go ahead and let's go ahead and do this. So it looks like, So we'll do the lab after we finish this lecture. All right, so this is what it looks like, right? So this is the destination network, and it is via this is the next hop. Next hop can be either a IP IP address or an exit interface, right? And then I'll show you both in the lab that we're going to configure later, all right? And then static route summarization. Route summarization combines multiple routes into a single route entry using a router subnet mask. So like /16/8/24, right? Reduces the number of routing entries, making the routing table smaller and more efficient. Use a larger subnet mask that encompasses multiple smaller routes or smaller networks. An example are /24, and you can combine these with the /16 since only the third octet or the /24 is what changes it to. So /16 will catch everything behind 192.168. Benefits: it simplifies routing, reducing memory usage, and improves router performance by minimizing overhead. Actually, I think that's all right. So let's cover this as well, and then we can demonstrate it in packet tracing. So the next hop interface. Next hop as an interface instead of an IP. The router's own exit interface can serve as the next hop. Direct connection. Useful when destination is directly reachable through the router's interface. Configuration specifies the interface, IP route, or destination network, subnet mask, and then the exit interface here instead of an IP. It reduces ARP lookups and can improve routing speed for directly connected networks. And this is how you do the default route. I'll demonstrate it as well on one of the routers. So a default static route directs all unspecified traffic to a designated next hop IP, often written as O.O.O.O/O/0, right? Providing a catch-all route for packets with an unknown destination, typically guiding traffic to an internet gateway. Use IP route O.O.O.O.O.O next hop, and then set it as the default route. It simplifies routing by covering all destinations, ideal for sending traffic out of a local network towards the internet. Default route/git. And that's it. So let's go ahead and get into this. Go ahead and talk just a little. So here. All right. So I'll show you all of them, right? And Control-T, and then we'll do remember IP route. Route followed by the destination, right? So let's say since we're able to communicate with it here, we'll say this, right? So it's IP route 2.68.20.0, and then the subnet mask is a /24, right? /24 here, and then it's the next hop, right? So if I can pass it to Eisen right here, I know it's going to get to Jerome, right? So 2.68.10.2. That's it, right? Let's configure. Let's try to ping. So it should be able to ping. We'll ping this G0/0/1 interface, right? Ping 2.68. Nope, wrong. Right? So the ping is successful pinging this interface here. Now, I did accidentally fat finger command did one this interface here. Would you be able to tell me why the pings failed? Right? You can see that it failed because it's 0 flat right? Would you be able to tell me why? I'll give you a second. Hopefully you have your answer. So it failed because there's no two-way communication, right? In And this is what ping confirms. So two-way communication is from this router, ping to here, and then this one's going to send it to here. So remember, the two cases, either there's no communication at all, or there's only one way. So for now, there's only one-way communication, because the route is able to get to here, right? But once it gets to here, it doesn't know this network exists at all, so it just drops it, and that's what they fail, right? Give me 1 second, I'll be right back. All right, I'm back. Sorry about that, guys. Let's see where we're. Just confirm that there's only one-way communication here. So this is set. So first we'll work our way this way, and then work our way going this way, right? And I'll show you the different types of routes that you can do, whether that be recursive, directly attached, or fully specified. And let me tell you what they are. So here is recursive. So recursive just means only using the IP address as the destination, right? Here we'll do it directly attached. Excuse me. We only specify the exit interface, right? So we'll do IP route. We'll do this network here. Remember, it's the destination, so where you're trying to get to. It is the subnet mask of that node, which everything here is a /24. Just /24 there. And here. You can use exit interface, right? So it's G, Ethernet, and then delete no, right? So not really too familiar with doing exit interface, but we'll see. It should be this one. So let's see. Do show IP route if it's in there. Yeah, it's in there. Disable this. This should send it to here. Alright, but this is just the directly attached, where it's just gonna explicitly specify the exit interface. And here we would do a fully specified, where it's where you specify not only the exit interface, but the IP address as well. See, and we'll do room here. We'll do this. This is the destination. 192.168.7.0, then the subnet mask, and then we will do a fully specified. So I think it should be. I think it's either exit interface first and then IP address, but I think it's IP address and exit interface. We'll try 2.68. We're going to use this next hub address right here. I got it wrong. It's exit interface. Here, 40 routers address. And then this is a fully specified route, right? So let's test connectivity. We'll do ping 192.168.7. See, and it 6 Let's just try it again. Let's try 2. And same thing. Succeed. So there's two-way communication between network 2 and network 1. And then here we will do a default route just to show you what that looks like. See, IP route, and then we'll do O.O.O. Remember, it's a catch-all. So if it doesn't find anything in the routing table that matches the destination address, it's going to send it to here. Right? We'll do just the next hop of 192.168.30.2. And now let's see if we're able to ping. And then let's do tracer to see where it actually stopped. Tracer 2.6. A trace route. So it's going to send it to here. And then it's just going to stay. Confirm. Alright, so let's troubleshoot on this one here. Are we able to ping? 192.6. We're able to ping there. Ping. 2. So confirm here. So this one's good. So we're looking at this one. So that looks to be fun. You see the extent of where the ping is to ISO. Alright, so this, we haven't configured this network with the next hop. So we show, yeah, we have, so that's why. Right? Conferencing. And then remember it's a slash before mask. So do that. And then the next hop is this one, right? This interface. Now let's try to ping again. Now it should work. Perfect. And it should go fast, right? So these are the next hops that we configured. So from here, next hop would be this interface right here. this next hop will be this interface. Right? And that's pretty much it for static routing. We've covered all the ways to actually do it, whether that be fully specified, where you do exit interface and XHop directly attached, where it's just the exit interface, as well as recursive, where it's just only the IP address, and the default route here as well. But yeah, that's pretty much all it. Thank you guys for tuning in, and see you in the next one.